All right, so Raoult's law we derived assuming ideal solutions, and so let's go ahead and use it for an ideal solution. Let's pick out one, actually not really at random. This is a solution that is sort of the really the most common let's use this for a solution that's sort of the prototypical ideal solution. We're going to use benzene and toluene. So you can see why this would form a nearly ideal solution. And so let's look at mole fraction of benzene. And that's going to go from 0 to 1. And so imagine the vapor pressure going up. And we know for either one of these that if we just take, for instance, let's just be specific, the vapor pressure of benzene is going to be equal to the mole fraction of benzene times the pure vapor pressure of benzene. So we can see that's going to be a nice straight line. And over here, we're going to have the vapor pressure of pure benzene. And we can draw a similar line for toluene. So we can see is these two curves. So here we have the toluene curve. I'll just call it P-tol. And here we have the benzene curve. I'll call it P-benz. And both of those, they're straight lines, actually not curves. They both lead to the pure vapor pressures. Okay, so this side is pure toluene, this side is pure benzene. If we add those two pressures together, we get the total pressure. And that's also a straight line, so we'll just call that P total. Make sure you keep in mind that Raoult's law applies to each individual line, and that if you want to get the total pressure, you have to add those two together. Right? Raoult's law does not apply directly to P total. All right, so that's using Raoult's law for ideal solutions. It's pretty straightforward. What we're next going to look at is how we can adapt this to real solutions. So let's first look at how real solutions look when we actually look at their vapor pressure. And so just for clarity, I'm just going to draw one component. So let's look at, let's go ahead and look at some component. And we know that if it followed Raoult's law, if it were behaving ideally, it would follow that dotted line. But what we often find is something that looks like this. The solution has a vapor pressure that does not follow that line, at least most of the way. And this is called a positive deviation from Raoult's law. And you can see it's the vapor pressure is higher. That's why I call it a positive. So this is pressure on this axis, and this is composition on this axis. So a couple of things to notice here. One is that when we're over really close to having pure B, it does behave ideally. And in fact, the closer we get, the more and more ideal it becomes. So it's kind of like the ideal gas law. The more the pressure, the lower the pressure, the more you become ideal in terms of your gas behavior. Well, the more pure you become, the more you become close to being ideal. So if you have the solvent, if you have nearly pure solvent, a very dilute solution, the solvent is going to follow Raoult's law. So let's just write that. The solvent closely follows Raoult in dilute solution. So if we go dilute enough, those two lines touch, and it will follow it exactly. Now this positive deviation means the vapor pressure is higher. This is something we see when we have unfavorable interactions between A and B. And it doesn't mean that A and B necessarily repel each other. It just means they attract each other less strongly than they attract themselves. So the AA and the BB interactions are stronger than the AB interactions. Conversely, we could have a different situation where we have a vapor pressure curve that looks basically the reverse of this. So imagine we have a different set of chemicals and ones where there's actually a favorable interaction. In this case, the vapor pressure curve will look something like this. So here, so this is still a pressure composition curve. So here, this is a negative deviation. Oops, I wrote negative. From Raoult's law, because the vapor pressure is lower, and this is favorable interactions. And if it will help you remember the difference between favorable and unfavorable, imagine the situation where you can see that in the liquid, molecules are going to be close together, right? And the gas are not. So it's the difference between being out on an open plaza and being in an elevator. So you think, okay, if I have to be with a skunk, would I rather be with a skunk in an elevator or in an open plaza? Well, the open plaza. So if you have an unfavorable interaction, you're going to want to go into the gas phase. On the other hand, if it's some cannoli, let's say it's cannoli, would you rather be on the open plaza with the cannoli 50 feet away, or would you rather be in an elevator? Well, that's a favorable interaction, right? You'd rather be in close contact. You'd rather be in the liquid phase. And so I don't know if that's going to help or not, but that's sort of how I think about it, is that because you have a close contact in the solution phase, if you have favorable interactions, you're going to favor the solution phase over the gas phase. We're going to actually put numbers on this later, but for now I just want you to have a qualitative sense of it. Okay, so favorable interactions is a negative deviation on Raoult's law. Okay. Oh, and we see something over here. What do we notice in this region over here? Oh, we're following Raoult's law closely. So this idea that the solvent follows Raoult's law very closely in dilute solutions, this is true whether you're unfavorable or favorable. So if you get a dilute enough solution, the solvent, and we better underline that we're talking about the solvent here, the solvent will follow Raoult's law as long as we're dilute enough. And so we should point out that since we're deviating from Raoult's law, this whole topic here, we could title this whole topic, this is all, let me rewrite this up here. This topic, both of these vapor pressure diagrams, we're talking about real solutions, right? Because if we were ideal solutions, we'd follow Raoult's law exactly, and clearly we're deviating. So these are real solutions. All right, so how do we actually handle real solutions numerically? How do we model this part of the curve where we're not behaving ideally? We do that using something called activity coefficients. So we need to use activities. Activities and activity coefficients. All right. So how do we use activity coefficients? Well, an activity coefficient, basically the activity replaces the mole fraction. So we can rewrite that the vapor pressure is equal to the pure vapor pressure. But instead of multiplying by the mole fraction, which is a form of concentration, we multiply by the activity. Okay, so this is the activity, and it's basically an effective concentration. Okay, once we write that, and we can immediately see, oh, so this is taking the place of mole fraction in real solutions. So this is actually true by definition. And then once we write that, we can say, oh, it must be for real solutions that the chemical potential of A is equal to the chemical potential of pure A plus RT log, well, for ideal solutions, we'd have mole fraction here. Well, so real solutions, we replace mole fractions with activity. So both of these, by definitions, are true for real solutions. And because we're basing this on deviation from Raoult's law, this is called the Raoultian standard state. Okay, so for gases, we've already talked about the 1 bar standard state, that the standard state for gases is to be at 1 bar pressure. Well, for solvents, when we use our Raoultian standard state, the standard state is pure stuff. Okay, so we're talking about deviations from pure stuff. And as we get closer and closer to pure stuff, we're going to get smaller and smaller deviations. Now we characterize these deviations by an activity coefficient. So we say the activity of some compound A is equal to the mole fraction times sort of I guess you could call it a fudge factor, which is the activity coefficient. So make sure that you keep the activity and the activity coefficient straight, right? You use activities to calculate activity, use activity coefficients to calculate activities from mole fractions. All right, one last thing I want to say before we move on is that we said on the previous slide that as we got more and more pure, actually you could just rewind this to see this, as we got more and more pure, we followed Raoult's law more closely. Well, if that's so, we can say the limit as the concentration goes to 1 of the activity coefficient, it's going to be equal to 1, right? As we get more and more pure, the activity coefficient goes to 1. If the activity coefficient goes to 1, we can plug that in over here, and our activity is equal to our mole fraction. And in that case, we're back to just following Raoult's law exactly. And that's what we said before. We follow Raoult's law exactly as we get to pure solvent. So this is the Raoultian standard state. So be prepared on Monday to be able to use data, vapor pressure data, to calculate both activities and activity coefficients in a Raoultian standard state. I just realized that I had A's on this page and B's on the previous page, and it doesn't really matter. Basically, you're going to use the Raoultian standard state for the solvent. On the left-hand side of the diagram, that will be one component. On the right-hand side of the diagram, that's going to be the other component. So whichever component you have more of is going to be the solvent, and that's the one you're going to use our Raoultian standard state.